here for now, and it's going to take us a while, we have to think about it pretty hard, is to calculate what this derivative is. All right, so we'll get started. And the way we get started is simply by plugging in the definition of the derivative. The derivative is the limit, as delta x goes to 0, of a to the x plus delta x minus a to the x divided by delta x. So that's what it is. And now, the only step that we can really perform here to make this into something a little bit simpler is to use this very first rule that we have here, that the exponential of the sum is the product of the exponentials. So we have here a to the x. So what I want to use is just the property that a to the x plus delta x is equal to a to the x, a to the delta x. And if I do that, I see that I can factor out a common factor in the numerator, which is a to the x. So we'll write this as the limit as delta x goes to 0 of a to the x times this ratio now, a to the delta x minus 1 divided by delta x. So far, so good. We're actually almost to some serious progress here. So there's one other important conceptual step which we need to understand, and this is a relatively simple one, and we actually did this before, by the way. We did this with sines and cosines. The next thing I want to point out to you is that you're used to thinking of x as being the variable, and indeed, already we were discussing x as being the variable and a as being fixed. But for the purposes of this limit, there's a different variable that's moving. X is fixed, and delta x is the thing that's moving. So that means that this factor here, which is a common factor, is constant. And we can just factor out of the limit. It doesn't affect the limit at all. A constant times the limit is the same as whether we multiply before or after we take the limit. So I'm just going to factor that out. So that's my next step here, a to the x, and then I have limit delta x goes to 0 of a to the delta x minus 1 divided by delta x. All right? And so what I have here, so this was by definition the derivative. So here's d by dx of a to the x, and it's equal to this expression here. Now, I want to stare at this expression and see what it's telling us, because it's telling us as much as we can get so far without some. So first, let's just look at what this says. So what it's saying is that the derivative of a to the x is a to the x times something that we don't yet know. And I'm going to call this something, this mystery number, m of a. So I'm going to make the label m of a is equal to the limit as delta x goes to 0 of a to the delta x minus 1 divided by delta x. All right, so this is a definition. So this mystery number, m of a, has a geometric interpretation as well. So let me describe that. It has a geometric interpretation, and it's a very, very significant number. So let's work out what it is. So first of all, let's rewrite the expression in the box using this shorthand for this number. So if I just rewrite it, it says d by dx of a to the x is equal to this factor, which is m of a, times a to the x. So the derivative of the exponential is this mystery number times a to the x. So we've almost solved the problem of finding the derivative of a to the x. We just have to figure out this one number, m of a, and we get the rest. So now let me first, let me point out two more things about this number, m of a. So first of all, if I plug in x equals 0, that's going to be d by dx a to the x at x equals 0. According to this formula, that's m of a times a to the 0, which is, of course, m of a. So what is m of a? M of a is the derivative of this function at 0, so m of a is the slope of a to the x at x equals 0 of the graph of a to the x at 0. So again, over here, if you looked at the picture, I'll draw the one tangent line in here, which is this one here. And this thing has slope, what we're calling m of 2. So if I graph the function y equals 2 to the x, I'll get a certain slope here. If I graph it with a different base, I'll maybe get another slope. And what we've got so far is the following phenomenon. If we know this one number, if we know the slope at this one place, we'll be able to figure out the formula for the slope everywhere else.